So this is shear example 5, continued, and we're on page 3. So again, I'll draw out the section, and this is completely ignoring the fact that it's to scale. The section is actually very thin, which is why this thin theory works. And the thin theory is that there's going to be no transverse shear stresses through the flanges. So that my drawing's not to scale because it shows that the flanges are very thick. But we're going to assume that in reality the flanges are really thin compared to the other dimensions. Now we did a cut there, and we also assume that we did a cut there as well. So that would be the first cut, and that would be the second cut. And the first cut and the second cut, Q1, which is going to be equal to Q2, or at least the moduluses definitely would be equal to each other, is going to be equal to V times B minus T over 2 times by T times by D minus T over 2, all divided by I. And let's just take that out. Let's just take out one of the halves. So let's just say it's half of V B minus T times T times D minus T over 2, all divided by I. So all I've done is rearrange that and taken out the half. So now if we wanted to do a cut at the third position, so let's draw that out again. So that's going to be our neutral axis, and then that one is going to be the so if we wanted to do our cut at the third position, so let's say that's 3, that effectively is saying why not take that portion out and work out the first moment of area of that about the neutral axis. So that's going to be B, that's going to be T, and then the distance from the neutral axis to that point is going to be, that dimension there is going to be D over 2, and then that dimension there is big T over 2. The distance from the centroid must be D minus T over 2, or D over 2 minus T over 2, which is that value there. So let's work out Q3. So Q3 is going to be equal to big V multiplied by B times T, because that's going to be the area, so area of the shaded bit is equal to B times T, and going to be multiplied by the centroid of that area to the neutral axis. and that is going to be d minus t over 2, and all of that is going to be over I. So now you can see that Q1 and Q2 is equal to now we've already said that Q1 and Q2 is going to be equal to B minus T, and that we have already said that T is very small. So B minus T is approximately equal to B, since T is very small, and therefore Q3 is approximately equal to Q1 plus Q2. So remembering back to the sketch that we did before showing the shear flow, we can see that whatever has passed through Q3 going upwards, whatever shear has flowed through Q3 going upwards there, so that's the shear flow at Q3, has in some respects been divided into two as it has flown out of the system towards the edges. So if that value there is Q3, then that value there is approximately Q3 over 2, and that value there is also approximately equal to Q3 over 2, or Q3 is approximately equal to Q1 plus Q2. So that's the second observation that we can make.